So this course is called Design and Analysis of Algorithms. So design is something that is easier to understand. We have a problem, we want to find an algorithm, so we are going to design an algorithm. But what exactly does analysis mean? So analysis means trying to estimate how efficient an algorithm is. Now there are two fundamental parameters that are associated with this. One is time. How long does the algorithm actually take to execute on a given piece of hardware? Remember, an algorithm will be executed as a program, so we'll have to write it in some programming language and then run it on some particular machine. And when it runs, we have all sorts of intermediate variables that we need to keep track of in order to compute the answer. So how much space does it take? How much memory does it require? Now, we will argue that in this course at least, we will focus on time rather than space. One reason for this is that time is a rather more limiting parameter in terms of the hardware. It's not easy to take a computer and change its speed. So if we are running algorithms on a particular platform, then we are more or less stuck with the performance that that platform can give us in terms of speed. Memory, on the other hand, is something which is relatively more flexible. We can add a memory card and increase the memory. And so, in a sense, space is a more flexible requirement. And so, we can think about it that way. But essentially, for this course, we will be focusing on time more than space. So, if we are looking at time, we have to ask how we measure the running time. So of course we could run our program on a given computer and report the answer in seconds or in milliseconds. But the problem with this is that the running time of an algorithm measured in terms of a particular piece of hardware will of course not be a robust measure. If we run it on a different computer or if we use a different programming language, we might find that the same algorithm takes different amount of time. More importantly, if we are trying to compare two different algorithms, then if we run one algorithm on one computer and the other on another computer, we might get a misleading comparison. So instead of looking at the concrete running time in terms of some units of time, it's better to do it in terms of some abstract units of how many steps the algorithm takes. So this means that we have to decide what a notion of a step is. So a step is some kind of a basic operation, a simple one-step operation that our algorithm performs. And the notion of a step, of course, depends on what kind of language we are using. If we are looking at a very low level, at an assembly language kind of thing, then steps involve moving data from the main memory to a register, moving it back, doing some arithmetic operation within the CPU, and so on. But typically, we look at algorithms and we design them and we implement them at a higher level. We use programming languages such as C, C++, or Java, where we have variables, we assign values to variables, we compute expressions and so on. So for the most part, we will look at basic operations as what we would consider single statements or steps in a high level language. So this could be an operation such as assigning a value x equal to y plus 1 or doing a comparison. If a less than b, then do. So checking whether a is less than b is one step for us. Now we could look at slightly more elaborate notions of steps. For example, we might assume that we have a primitive operation to actually exchange the values in two variables, though we know that to implement this we actually have to go by a third temporary variable. What we will see is that we will come up with a notion which is robust so that the actual notion of a basic operation is not so relevant because we will be able to scale it up and down according to what notion we choose to focus on. The other important thing to realize, of course, is that the algorithm will take a different amount of time depending on the size of the problem that it is presented with. It's quite natural and obvious that if we are trying to sort an array, it will take longer to sort a large array than it will to sort a short array. So we would like to represent the efficiency of an algorithm as a function of its input size. So if the input is of some size n, then it will take time t of n, where t will be a function depending on the input n. But even this is not immediately an obvious definition because not all inputs of size n are going to take the same amount of time. Some inputs will take less time, some inputs will take more time. So what do we take? Right? So it will turn out that the notion that we will typically look at is to look at all the inputs of size n and look at the worst possible one, the one that takes the longest time. Right? So this is called a worst case estimate. It's a pessimistic estimate, but we will justify it as we go along. But this is what we mean now. When we are looking at the time efficiency of an algorithm, what we mean is what is the worst possible time it will take on inputs of size n and express this as a function of n. So before we formalize this, let's just look at a couple of examples and get a feel for what efficiency means in terms of practical running time on the kinds of computers that we have available to us. So let us start with sorting, which is a very basic step in many algorithms. So we have an array with n elements, and we would like to arrange these elements, say in ascending or descending order, for further processing. Now a naive sorting algorithm would compare every pair of elements, more or less, and try to determine how to reorder them. This would take time proportional to n square because we are comparing all pairs of elements. On the other hand, we will see soon in this course that there are much cleverer sorting algorithms which work in time proportional to n log n. So we can go from a naive algorithm which takes time n square to a better algorithm which takes time n log n. So what we have really done is we have taken a factor of n and replaced it by a factor of log n. So this seems a relatively minor change. So can we see what the effect of this change is? So one way to look at this is to actually look at concrete running times. We said that we will not look at running times as measuring the efficiency of the algorithm, but of course the efficiency of the algorithm does have an impact on how long the program will take to execute, and therefore on how usable the program is from our practical perspective. So if you take a typical CPU that we find on a desktop or a laptop, which we have these days, it can process up to about 10 to the 8 operations. These are these basic operations in a high level language like an assignment or checking whether one value is less than another value. We can say that it can do about 10 to the 8 operations. Now this is an approximate number, but we need to get some handle on a number so that we can do some quantitative comparisons of these algorithms. So it's a useful number to have for approximate calculations. Now one thing to remember is that this number is not changing nowadays. We used to have a situation where CPUs were speeding up every 1.5 years, but now we have kind of reached the physical limits of current technology. So CPUs are not speeding up. We are using different types of technologies to get around this, parallelizing, multi-core and so on. But essentially the sequential speed of a CPU is stuck at about 10 to the 8 operations per second. So now when we take a small input, supposing we are just trying to rearrange our contact list on our mobile phone, we might have a few hundred contacts, maybe 1,000 contacts, maybe even a few thousand contacts. If we try to sort our contact list, say by name, it really would not make much difference to us whether we use an n square or an n log n algorithm. Both of them will work in a fraction of a second, and before we know it, we will have the answer. But if we go to more non-trivial sizes, then the difference becomes rather stark. So consider the problem of compiling a sorted list of all the mobile subscribers across the country. It so turns out that India has about 1 billion, that is 10 to the 9 mobile subscribers. This includes data cards, phones, various things, but these are all people who are registered with some telecom operator and own a SIM card. Okay, so this is the number of SIM cards which are in active use in India today. So suppose we want to compile a list of all owners of SIM cards in India in some sorted fashion. Since we have 10 to the 9 subscribers, if we run an n square algorithm, this will take 10 to the 18 operations, because 10 to the 9 square is 10 to the 18. Now 10 to the 18 operations per second, since we can do only 10 to the 8 operations in 1 second, will take 10 to the 10 seconds. So how much is 10 to the 10 seconds? Well, it's about 2.8 million hours. Okay? It's about 115,000 days. And that's about 300 years. So you can imagine that if we really want to do this using an n square algorithm, it would really not be practical, because it would take more than our lifetime, more than several generations in fact, to compute this on the current hardware. On the other hand, if we were to move to the smarter n log n algorithm, which we claim we will find, then it turns out that sorting this large number of phone users takes only 3 times 10 to the 10, because the log to the base 2 of 10 to the 9 is 30. it's useful to remember that 2 to the 10 is 1000. So log to the base 2 of 1000 is 10. Now since logs add, 1000 times 1000 is 10 to the 6, right? So the log of 10 to the 6 is 20. Log of 10 to the 9 is 30. So 30 into 10 to the 9, n log n is 3 times 10 to the 10. So this means that it will take about 300 seconds. So it will take about 5 minutes. Now 5 minutes is not a short time. You can go and have a tea and come back. But still, it will get done in a reasonably short amount of time so that we can then work with this useful information and go on. As opposed to 300 years, which is totally impractical. So let's look at another example. So supposing we are playing a video game. Right? So this might be one of these action type games where there are objects moving around the screen and we have to identify certain objects, shoot them down, capture them, whatever. So let's assume that as part of the game, in order to compute the score, it has to periodically find out the closest pair of objects on the screen. So now how do you find the closest pair of objects among a group of objects? Well, of course, you can take every pair of them, find the distance between each pair, and then take the smallest one. Right? So this will be an n-square algorithm. Right? So you compute the distance between any two objects, and then after doing this for every pair, you take the smallest one. Now it turns out that there is a clever algorithm, again, which takes time n log n. So what is this distinction between n square and n log n in this context? Now on a modern kind of gaming computer with a large display, it is not unreasonable to assume that we could have a resolution of say 2500 by 1500 pixels. If we have one of these reasonable size 20-inch monitors, we could easily get this kind of resolution. So we will have about 3.75 million points on the screen. Now we have some objects placed at some of these points. So let us assume that we have 5 lakh objects, 500,000 objects placed on the screen. So if we were to now compute the pair of objects among these 500,000 which are closest to each other, and we use the naive n-square algorithm, then you would expect to take 25 times 10 to the 10 steps, because that is 5 into 10 to the 5 whole square. 25 into 10 to the 10 is 2500 seconds, which is around 40 minutes. Now if you're playing a game, an action game in which reflexes determine your score, obviously each update cannot take 40 minutes. That would not be an effective game. On the other hand, you can easily check that if you do an n log n calculation for 5 into 10 to the 5, you will take something like 10 to the 6 or 10 to the 7 seconds. So this will be a fraction of a second, 1/10 to 1/100th of a second, which is well below your human response time. So it will be essentially instantaneous. So we move from a game which is hopelessly slow to one in which it can really test your reflexes as a human being. Right? So we have seen in these two examples that there is a real huge practical gulf between even something as close to each other as n log n and n square. The size of the problems we can tackle for n square are much smaller than the size of the problems we can tackle for n log n. So when we look at these functions of n, okay, typically we will ignore constants. Now this will partly be justified later on by the fact that we are not fixing the basic operation, but essentially by ignoring constants we are looking at the overall function of the efficiency as a function of n as it increases, right? So this is what we call asymptotic complexity. As n gets large, how does the function behave? So for instance, supposing we have some function which grows like n square with a large coefficient and something which grows like n cubed with a coefficient of 1. Initially it will look like n square, say 5000 n square is much more than n cubed. But very rapidly, say at 5000, right? At 5000 we'll have both will be 5000 cubed. And beyond 5000, the function n cubed will grow faster than the function 5000 n square. Right? So there will be a point beyond which n cubed will overtake n square, and after that it will rapidly pull away. Right? So this is what we would typically like to measure. We would like to look at the functions as functions of n without looking at the individual constants, and we will look at this a little more in detail. So since we are only interested in orders of magnitude, we can broadly classify functions in terms of what kind of functions they look like. Right? So we could have functions which are proportional to log n, functions which are proportional to n, n square, n cube, n to the k, which is, so any n to the fixed k is a polynomial. So we can call all these functions we will look at as polynomial, right? So these are polynomial complexity. And then we could have something which is 2 to the n. If 2 to the n essentially comprises of looking at all possible subsets. So these are typically the brute force algorithms where we look at every possibility and then determine the answer. Right? So we have logarithmic, polynomial, and exponential functions. So what do these look like in terms of the numbers that we were talking about? So if you look at this chart, the left column varies the input size from 10 to the 1 to 10 to the 10. And then each column after that is a different type of complexity behavior, okay, as a function which ignores constants and only looks at the magnitude. So we have log n, then we have something which is polynomial n square, n cube. In between we have n log n, which we saw before, and then we have these two exponential functions which are 2 to the n and n factorial. Okay. So now in this we are trying to determine how efficiency determines practical usability. Okay. So now if you look at this, we said that we can do 10 to the 8 operations in 1 second. So maybe we are willing to work up to 10 seconds. So 10 to the 9 operations is about the limit of what we would consider efficient. 10 to the 10 operations would mean 100 seconds, which would mean 2 minutes, and maybe 2 minutes is too long. Okay. So now clearly if we are looking in a logarithmic scale, there's no problem. Up to 10 to the 10, right, we can do everything in about 33 steps, which will take very, very little time. Now in a linear scale, given that we are expecting 10 to the 9 as our limit, this becomes our limit, right? So we can draw a line here and say that below this red line, okay, things are impossibly slow. N log n is only slightly worse than n. So we can do inputs of size 10 to the 8 because n log n for 10 to the 8 is something proportional to 10 to the 9. Now there's this huge gulf that we saw. If we move from n log n to n square, then the feasibility limit is somewhere between 10 to the 4 and 10 to the 5. Okay, because the 10 to the 5 we've already reached a running time of 10 to the 10, which is beyond what we want. And now if we move to n cubed, then the feasibility limit drops further, so we can't go beyond about an input size of 1000. Okay? So we can see that there's a drastic drop, and when we come to exponentials, really beyond some trivial things of size 10 or 20, we can't really do anything. Anything which is even 100 will be impossibly slow. Right? So we have these kind of this sharp dividing line of feasibility. Okay? And so we can see that it is important to get efficient algorithms, because if we have inefficient algorithms, even if we think that they work correctly, they will not be able to solve problems of any reasonable size. Okay? And when we are looking at computational algorithms running on a PC, we would really expect our input sizes to be hundreds, thousands, and much more. Right? So when we are sorting things, we really do expect large volumes of data. If you want to look at voters lists or population data or data coming out of, say, a biology experiment about genetic material. Now these things are typically very large volumes of data. So it's really important to get the best possible algorithm to do these things. Otherwise, the problem at hand will not be effectively solvable.